friends, welcome to the lecture of linear algebra. In last lecture we have seen what is a diagonalizable operator, and from this we have seen what is a diagonalizable matrix. Any operator T is said to be diagonalizable if there exists a basis curly v for V such that the matrix of linear operator T with respect to that basis is a diagonal matrix. Or also we can define diagonalizable operator as a linear operator defined on a finite dimensional vector space V is said to be a diagonalizable if there is a basis curly V for V such that each vector of this basis is a characteristic vector of linear operator T. Okay, now today we have to see what is the relation between the diagonalizable operator or diagonalizable matrix and the algebraic and geometric multiplicity of each eigenvalue of a operator T. Okay. Before that, let us see. Let T be a diagonalizable operator. Diagonalizable operator on a n-dimensional vector space V. Okay. So here given that T be a diagonalizable operator on a n-dimensional vector space V, and let C1, C2, sorry, lambda 1, lambda 2, lambda 2 up to so on lambda k are distinct eigenvalues of T, are distinct eigenvalues of T. As given that T be a diagonalizable operator, then from the definition of diagonalizable operator, there is a basis curly V for V such that the matrix of linear operator T with respect to ordered basis curly V is a diagonal matrix. Okay, as it is a diagonal matrix. Okay, now and the diagonal entries of this matrix are diagonal entries of it are or the diagonal entries of this matrix are C1, C2 up to so on Ck. That is, diagonal entries of this matrix are the scalars Ci, are the scalars Ci, where each Ci is repeated di times. Okay, di times. So as matrix of T with respect to linear operator T with respect to ordered basis B is a diagonal matrix, then Aij will be equal to 0 for each I not equal to j. Then there are only the diagonal entries present in the given diagonal matrix which are non-zero. So these diagonal entries are nothing but these Ci's, where each Ci is repeated di times. Since here we don't know that where this k is equal to n or not. If each lambda 1, lambda 2 up to so on lambda k is distinct, this k is nothing but n. But if eigenvalues are not distinct, distinct. If k equal to n, then each eigenvalue is distinct. But if k is not equal to n, then there are some lambda I which are repeated. Okay. Sorry, here we have to take lambda I, where each lambda I is repeated di times, since eigenvalues are lambda. Okay. Now, then the matrix has following block form representation. Okay. Here each lambda I is distinct. That is lambda 1, lambda 2 up to so on lambda k is distinct. But we don't know that k is equal to n or not. If k equal to n, then there is no problem. But if k is less than n, then there are some lambda I which are repeated. Okay. Now here the matrix A, which is nothing but matrix of linear operator P with respect to ordered basis B, which is nothing but this matrix is a here diagonal matrix since it is a diagonalizable operator. Therefore, this matrix contains first one lambda 1 I1 0 0 to so on 0 0 lambda 2 I2 0 to so on 0 0 0 0 and up to so on lambda k I. And this matrix is a matrix of order n cross n since it is a linear operator on n dimensional vector space. Okay, now where each ij is a identity matrix of order dj cross dj. Since here each lambda I is repeated di times, therefore each ij is a dj cross dj matrix. Since each lambda 1 is repeated d1 times, lambda 2 is repeated d2 times, similarly lambda k is repeated dk times. So its corresponding identity matrix is a matrix of order dj cross dj. Okay, now we know that the characteristic polynomial of a linear operator P is given by f of x is equal to determinant of xi minus matrix A. So which is nothing but determinant of xi minus A is equal to first one xi is nothing but x comma ax 0 0 so 0 0 x so 0 0 and 0 minus xi minus a, or here we have taken eigenvalues as okay xi minus a, but here it is nothing but a matrix is nothing but lambda 1 I1 0 so on 0 0 lambda 2 I2 on 0 0 0 lambda k I2. Okay, this one is a lambda k I. So here we get, and now we have to take its determinant. Okay, so xi minus a and its determinant. So which is nothing but determinant of x minus lambda 1 of I1. Here also I1, I2, so on, x into I. So which is nothing but x minus lambda 1 into I1, 0, 0, so on 0, 0, x minus lambda 2 into I2, here 0. 0 0 0 x minus lambda k into I, where this is a determinant of order n cross n. Now we have to find its determinant, but we know that the determinant of diagonal matrix is nothing but the product of its diagonal entries, which is nothing but x minus lambda 1 into I1 into x minus lambda 2 into I2 and so on x minus lambda k into ik, which is the determinant of xi minus a. But here each I1 is a square matrix of order d1 cross d1, where I1 is a square matrix of order d1 cross d1, I2 is a square matrix of order d2 cross d2, and so on. Ik is a matrix of order dk cross dk. Then its determinant is here as x minus lambda 1 into I1. I1 is a determinant of order d1 cross d1. Then this x minus lambda 1 is repeated d1 times. Similarly, x minus lambda 2 is repeated d2 times. Since from each row there is one x minus lambda 1, as there are d1 lambda 1, d1 such a terms, then x minus lambda 1 to the power d1, x minus lambda 1 to the power d1. Since I1 is a square matrix of order d1 cross d1, then its determinant contains x minus lambda 1 d1 times. Similarly, x minus lambda 2 to the power d2 up to so on x minus lambda k to the power dk. So this one is the characteristic polynomial of a linear operator xi minus a. Now in last lecture, we have seen what is an eigenspace. That is, eigenspace W lambda is nothing but it is the eigenspace with respect to eigenvalue lambda, and which is nothing but the collection of its characteristic vector. Collection of characteristic vector is nothing but its kernel. That is, eigenspace is actually nothing but kernel of t minus lambda I. Since in eigenspace we take all the characteristic vectors with respect to with respect to eigenvalue lambda and which is nothing but kernel of t minus lambda I, and dimension of w lambda is nothing but dimension of kernel of t minus lambda I is nothing but nullity of t minus lambda I, and nullity of t minus lambda I is denoted by this symbol. Okay, so which is nothing but nullity of linear operator t minus lambda I, which is denoted by this symbol. Okay, t minus lambda. But in last lecture we have seen dimension of eigenspace w lambda is nothing but its geometric multiplicity of a eigenvalue lambda. So geometric multiplicity of lambda is nothing but nullity of t minus lambda. Okay, now here from this, here the rank of matrix P or A minus lambda 1 into is equal. So this one is a diagonal matrix. Here x minus lambda 1 is repeated d1 times. If we subtract lambda 1 from this matrix, then here we get all these terms will be equal to 0, and its rank is nothing but d1, d2 plus d3 plus up to so on dk. Okay, that is its, and d1 plus d2 plus up to so on dk is nothing but n, its order. Here actually d1 plus d2 plus up to so on dk is nothing but its original order n. That is, here matrix is of order n cross n. Here lambda 1 is repeated d1 times, lambda 2 repeated d2 times, up to so on lambda k repeated dk times, and d1 plus d2 plus dk is nothing but our n. And if we find out the rank of matrix A minus lambda 1 9, then these d1 terms are 0 and the remaining terms are non-zero. Then its rank will be equal to n minus d1, since d1 plus d2 plus up to so on dk will be equal to n, and now d1 becomes 0. That is, lambda 1, all these terms are 0. Then its rank will be equal to n minus d1, which is equal to n minus d1. And by rank nullity theorem, rank is denoted by this symbol. Okay, so rank of A minus lambda 1 I plus nullity of A minus lambda 1 I is equal to dimension of its domain, and dimension of dimension of a given linear operator is V, which is of n dimension, which is equal to n. Okay, now here given that rank of a minus lambda 1 I will be equal to n minus d1. N minus d1 plus nullity of a minus lambda 1 I is equal to n get cancelled, and which is nothing but n rank of a minus lambda 1 I is equal to d1. But d1 is nothing but the algebraic multiplicity of eigenvalue lambda 1. Since lambda 1 is repeated d1 times, and we know that what is algebraic multiplicity? Algebraic multiplicity of a eigenvalue is nothing but the number of times it appears in its characteristic polynomial as a root. So here lambda 1 is repeated d1 times. Then algebraic multiplicity of lambda 1 is d1, which implies nullity of a minus lambda 1 I is equal to algebraic multiplicity of eigenvalue lambda 1. But nullity of p minus lambda I, which is nothing but the nullity of a minus lambda I, is nothing but the geometric multiplicity of eigenvalue lambda. From this, nullity of a minus lambda 1 I is nothing but the geometric multiplicity of eigenvalue lambda 1, which implies geometric multiplicity of lambda 1 is equal to algebraic multiplicity of lambda 1. This is for particular lambda 1. Similarly, we can find out it for all the eigenvalues. So here geometric. So here similarly, here geometric multiplicity of lambda I is equal to algebraic multiplicity of lambda I whenever I become 1 to t, which is true for all the lambdas, and this is true from if t is a diagonalizable operator. So any operator t, if given that any operator t is a diagonalizable operator, then the geometric multiplicity of each eigenvalue will be equal to its algebraic multiplicity. Then only the given linear operator t is a diagonalizable. If the geometric multiplicity of some lambda 1 is not equal to lambda I is not equal to its algebraic multiplicity, then the given linear operator is not a diagonalizable operator. From this we conclude one remark: T is a diagonalizable operator. Diagonalizable operator if and only if geometric multiplicity of lambda is equal to algebraic multiplicity of lambda for all eigenvalue lambda of linear operator t. Then only the given linear operator is diagonalizable. If there exists one lambda which have geometric multiplicity is not equal to algebraic multiplicity, then the corresponding linear operator is not a diagonalizable operator. So we can also find out whether given linear operator is diagonalizable or not by this method. Okay? Now, here we have seen the diagonalization of linear operator. Now let us see what is a diagonalizable matrix. Let A be a square matrix, a matrix of order n over this field, yes, then A is said to be diagonalizable if there exists a non-singular matrix, exists a non-singular matrix matrix P such that P inverse AP equal to D, where D is a diagonal matrix, and the diagonal entries of D entries of D are the eigenvalues of matrix. So when we say that the given matrix A is a diagonalizable matrix, if suppose the matrix A is a square matrix of order n over the field here, then this matrix A is said to be a diagonalizable matrix. If there exists a non-singular matrix P, non-singular means if determinant is not equal to 0. That is, there exists a non-singular matrix P such that P inverse AP is nothing but D, where this D is a diagonal matrix, and the diagonal entries of this matrix are nothing but the characteristic values of the matrix A. Okay. Now we will give one example of matrix. Okay. Example. Let A equal to -2 -3 2 1 -6 -1 -0. Iterate similarity transformation that diagonalizes this matrix. So here we have to find out the matrix P. Okay. Given that A be a square matrix of order 3. Now we have to check whether this given matrix is a diagonalizable matrix or not by previous definition. We have seen how we will check the given matrix is a diagonalizable or not. Here we have to find out one non-singular matrix P such that P inverse AP will be equal to D, where the diagonal entries of this D is nothing but the eigenvalues of this matrix A. To check, so we have to first find the eigenvalues of the matrix A, and how will you find out its eigenvalues? First we have to find out its characteristic equation, that is determinant of xi minus a will be equal to 0. Okay. The characteristic equation of A is given by determinant of xi minus a is equal to 0, or a minus xi is equal to 0. Okay, now determinant of xi minus a, determinant x into I, x minus a is nothing but its diagonal is 2, minus or minus plus x plus 2 minus 2 plus minus 2 x minus 1 plus 6 plus 1 plus 2 into x. So which is equal to 0. Now here x plus 2. Now we have to find out its determinant. Okay. X plus 2, x minus 1 into x, x into x minus 1. Okay. Minus 1 plus 2 into minus of 2x minus 6. Minus 2x minus 6 plus 3 into minus 4 minus of x minus 1. Minus 4 minus of x minus 1. Okay. Which is equal to 0. Which implies x plus 2 into x square minus x minus 12 minus of 4x minus 12 minus 12 minus of 3x plus 3 is equal to 0. Which implies x cube minus x square minus 12x plus 2x square minus 2x minus 24 minus 4x minus 3x minus of 7x minus 12 minus 12 minus 24 plus 3 minus of 21 is equal to 0. Which implies x cube minus x square plus 2x square plus x square minus 12 minus 2 minus 14 minus 7 minus 14 minus 7 minus of 21 years. Okay. Minus here minus 24 here plus x cube minus x square minus 12x plus 2x square minus 2x minus 24 plus again minus 24 here minus 10 minus 24 minus 24 minus of 48 minus 48 plus 3 minus 48 plus 3 minus of 45 will be equal to 0. So this one is the characteristic polynomial of a given linear operator. Sorry. Here is a this one is the minus 24, minus 12, minus 12, minus 24, minus 24 plus 3, minus 21, minus 24, minus 21, minus 25, which is equal to 0. So this one is the characteristic polynomial of a given linear operator. Now we have to find out its roots. Okay. Check whether one is a root, 1 plus 1, 1 minus 2 minus 21, 2 minus 21 is 90, 90 minus 45 not equal to 0. Similarly, 2 is not a root. Let us put x is equal to 5. X equal to 5 means 5 cube is 125 plus 5 square is 25 minus 21 into 5 minus of 105 minus of 45 Let us check whether it is equal to 0. 125 plus 25, 150 minus 105 minus 45, 150. It is equal to 0. Then 5 is the root of this given polynomial, characteristic polynomial. So, by synthetic division method, 1 minus 21 and minus of 45. Okay. So here 1, 5 into 1, 5, 5 plus 1, 6, 6 into 5, 30, minus 21 plus 30, 9, 9 into 5, 45, which is equal to 0. So, its roots are x minus 5 into x square plus 6 lambda plus 9 is equal to 0, which is nothing but x minus 5 into this one, x square plus 6 lambda plus 9, which is nothing but x plus 3 square, x plus 3 square is equal to 0, since x square plus 2 into 3x, 2 into 3x, sorry, x square plus 6x plus 9 equal to 0. X 2 into 3x, 6x plus 3 square is 9, which implies x equal to 5 comma minus 3 comma minus are the eigenvalues of matrix A. So these are the eigenvalues of the matrix A. Now we have to find out the eigenspace, that is matrix P, non-singular matrix P. Before that, let us find out its characteristics vectors. Okay, let x1 be the characteristic vector corresponding to eigenvalue 5. Okay, that is, let us take this 5 as lambda, that is eigenvalue. So, as x1 is the characteristic vector, then a of lambda is equal to lambda, that is now we have to find out ax1 is equal to lambda at x1, which implies a minus lambda of I x1 is equal to 0. But here a is nothing but minus 2, 2 minus 3, 2, 1 minus 6, minus 1 minus 2, 0, minus lambda. Lambda 1 is, sorry, lambda is here 5. 5, 0, 0, 0, 5, 0, 0, 0, 5. And we need to this x1, take this x1 as a xyj, and it is equal to 0, 0 and 0. Okay, so which is nothing but now minus 2 minus 5 minus 7, 2, 0, 2 minus 3, 2, 1 minus 5 minus 4 minus 6 as it is, minus 1 minus 0 minus 1, minus 2 minus 0 minus 1, 0 minus 5 minus of 5 into xyj is equal to 0, 0, 0. Now find out the corresponding equation. Minus of 7x plus 2y minus 3z is equal to 0. 2x minus 4y minus 6z equal to 0. Minus of x minus 2y minus of 5z will be equal to 0. Okay, now we have to find out the values of x, y, and z which satisfies these equations. Okay, if we take x equal to minus 1, y equal to minus 2, and z equal to 1, then let us check whether it satisfies these three equations. as x equal to minus 5, which is nothing but 7 minus 4. Okay, 7, sorry, 7 minus 4 minus 3. 7 minus 4, 3, 3 minus 3, which is equal to 0. Similarly, x equal to minus 1, minus 2, plus 8, minus 6, minus 6 minus 2 minus 8 plus 8, which is equal to 0. Okay, similarly, x equal to minus 1, which is 1, y equal to minus 2, which is plus 4, z equal to 1, which is minus 5, which is equal to 0. So, if we take x equal to minus 1, y equal to minus 2, and z equal to 1, then it goes this equation. Then what is the value of x, y, z is x equal to y, x equal to minus 1, y equal to minus 2, and z equal to 1. So the characteristic vector x1 is nothing but minus 1, minus 2, and 1. So this one is the characteristic vector corresponding to eigenvalue 5. Now similarly we have to find out the characteristic vector corresponding to eigenvalue minus 3. So which is nothing but let x be the characteristic vector corresponding to eigenvalue minus a. By the definition of characteristic vector, a minus minus of minus plus 3i is equal of x is equal to 0, which implies a plus 3i minus 2 plus 3 minus 1, 2 minus 3, 2, 1 plus 3, 4, minus 6, minus 1, minus 2, 0 plus 3, 3 of x. Let us take this case as x, y, z, and which is equal to 0, 0, 0. Okay. So which implies minus of x. We forget. Now, let us take R2 minus 2R1 and R2 is changing to R2 minus 2R1 and R3 is changing to R3 plus R1. Then we get minus 1, 2 minus 3, 2. 2 minus 2, 0. 4 minus 4, 0. Minus 6 plus 6, 0. Minus 1. Sorry, we are doing this small. Minus 1. Minus 2 plus 3, it is a plus 1. Okay. It is a plus 1. 2 minus 2, 0. 4 minus 2, 0. Okay. Now, minus 1 plus 1, 0. Minus 2 plus 2, 0. 3 plus 3 minus 3, 0. Of x, y, z is equal to 0, 0, 0. So, which is nothing but x plus 2y minus 3z is equal to 0. Now, let us take z equal to 0 and y equal to minus 1, which implies x equal to x plus y is minus 1. Minus 1 is nothing but x minus 2 equal to 0, which implies x equal to 2. And in second condition, take z equal to 1 and y equal to 0, which implies yes, y 0 minus 3 equal to 0, which implies x equal to 2. Now, from this, if x equal to 2, y equal to minus 1 and z equal to 0, we will check whether it will be equal to 0. X equal to 2. 2 y is minus 1. 2 minus 2, 0, and z is already 0. Therefore, 0 is equal to 0. Second condition. Let us check z equal to 1. It is minus 3. Y equal to 0 is 0. And x equal to 3. 3 minus 3 is again 0. Then the characteristic vectors corresponding to these eigenvalue minus 3 are. Suppose x1, x2, and x3 are the characteristic vectors corresponding to eigenvalue minus 3. This one is the x1. So x2 is nothing but first one is 2, y is minus 1, and z is 0, and x3 is nothing but 3, 0, 1. So here we have find out the characteristic vector corresponding to both the eigenvalues 5 and minus 3. Now let us construct the matrix P. P is nothing but the take P as these indices minus 1, minus 2, 1, 2, minus 1, 0, and 3, 0. Now we will check first whether this matrix is a non-singular or not. Since we have to find out the matrix P, which is non-singular, and P inverse AP will be equal to D, then the corresponding matrix A is a diagonalizable matrix. So, determinant of P is equal to minus 1, 2, 3, minus 2, minus 1, 0, 1, 0, 1. And its determinant is nothing but minus 1 into minus 1. Minus of 2 into minus 2 plus 3 into minus 2 into 0 minus of minus 1 plus 1. So which is equal to minus 1 into minus 1 1 minus into minus 2 plus 4 plus 3 1 plus 4 plus 3 which is equal to 8, which is not equal to 0. Therefore P is non-singular and determinant of P is equal to 8. Now we have to find out P inverse. And how will we find out P inverse? We have already seen adjoint by adjoint method. P inverse is nothing but transpose of adjoint of a matrix A, matrix P. So first we have to find out the adjoint of a matrix P. And adjoint of a matrix P is nothing but first adjoint of matrix P. That is, we have to find out first its minor and multiply it by minus 1 to the power. If suppose Aij is the, if we have to find out the cofactor of element Aij, then cofactor of element Aij is nothing but minor of Aij into minus 1 to the power I plus j. So cofactor of this A11. So here we have to delete this row, first row and first column. Then it is nothing but minus 1. Minus 1 is its minor, and it is multiplied by minus 1 to the power 1 plus 1 since it is A11. So minus 1 to the power 1 plus 1, which is a minus 1 square, which is 1. So it is nothing but minus of 1. Okay. Similarly, now we have to find what is 2 minus 2 into minus 1 to the power 1 plus 2, which is minus 1. Minus 1 into minus 2, which is 2. 3. 0 minus 1 minus plus 1. Minus 2 minus 2. Minus 2. Minus of 1 minus of 3 minus 1 minus 3 minus 4 into 1 to the power minus 1 to the power 4, which is 1 minus 1 to the power minus 4 0 minus 2 2 0 minus 2 minus 2 0 minus 1 minus plus 3 0 minus 1 minus plus 6, but it is 3 minus 6. -1 plus 1 -1 plus 1 plus 1 plus 1. This is the adjoint of matrix. So which implies P inverse is nothing but 1 upon that is adjoint of sorry. First we have to take its transpose of matrix. Adjoint of transpose. Sorry. Adjoint of matrix P is nothing but cofactor matrix and its transpose. Sorry. Adjoint of matrix P is nothing but first we have to find out the cofactor matrix of the given matrix and its transpose is nothing but the adjoint of matrix P. So here we have to find out the adjoint of P and now for that we have to take its transpose. -1 2 1 -2 -4 2 3 -6 1. This is the adjoint of a matrix P. Okay, now this one is the adjoint of P and P inverse is nothing but by adjoint method adjoint of matrix P divided by determinant of P. Determinant of P is nothing but 8 into -1 -2 3 2 -4 -6 and 1 2 5. So which is the P inverse. Now we have to check whether P inverse AP is a diagonal matrix or not. Okay. If P inverse AP is a diagonal matrix, then the diagonal entries of that matrix P inverse AP are nothing but the eigenvalues of it. Then the corresponding matrix A is a diagonalizable matrix. Consider P inverse A which is equal to 1 upon 8 into P inverse -1 -2 3 2 -4 -6 1 2 5 and matrix A is -2 2 -3 matrix A 2 1 -6 -1 -2 0 and matrix P is nothing but where is P? P is nothing but -1 2 3 -1 2 3 -2 -1 0 -2 -1 0 and 1 0 1. Okay, now first take multiplication of these two matrices and which is nothing but -1 into -2 plus 2 -2 into -2 -2 into 2 -2 3 -3. Okay, now -1 -2 -6 sorry -2 -6. Okay, now -3 -3 -1 3 -2 plus -2 into -6 plus 1 which is 0. Okay, and 2 -4 -4 -8 -6 into -1 plus 6. Okay, 2 into 2 4 -4 minus plus 12 into -3 -6 -4 into -6 plus 24 -6 into 1 into -2 2 into 2 4 5 into -1 -5. Okay, 1 into 2 2 into 1 5 into -10 1 into -3 2 into -6 which is 0 and matrix -1 2 3 -2 -1 0 1 0 1 which is equal to 1 by a into 2 minus 4 minus 2 minus 2 minus 3 minus 5 minus 2 minus 2 minus 2 minus 2 minus 2 minus 4 minus 6 minus 10 3 plus 12 15 minus 4 minus 8 minus 12 plus 6 minus 6 4 minus 4 0 which is 12 minus 6 plus 24 18 minus 4 minus 2 minus 5 minus 7 4 minus 7 minus 3 2 plus 2 4 4 minus 10 minus 6 minus 3 minus 12 minus of 15 into minus 1 2 3 minus 2 minus 1 0 1 0 1. Now we have to take the multiplication of these two matrices. Okay, now minus of 5 into minus 1 5 minus 10 into minus 2 plus 20 15 into 1 plus 15. Okay, minus 5 2 minus of 10 minus 10 into minus 1 plus 10 15 into 0 0 minus 5 into 3 minus of 15 minus 10 into 0 0 15 into 1 plus 15 minus 6 into minus 1 plus 6 12 into minus 2 minus of 24 18 into 1 plus 8 minus 6 plus minus 6 into 2 minus 1 12 into minus 1 minus 1 18 into 0 0 minus 3 into 3 minus of 9 sorry minus 3 into 3 minus 9 sorry. Minus 6 into 3 minus of 18 12 into 0 0 plus 18 into 1 plus 8 minus 3 minus 1 plus 3 minus 6 minus 2 plus 12 minus of 15 okay minus 3 minus 2 minus 6 minus 3 2 minus 6 minus 1 plus 6 minus 15 into 0 0 minus 3 into 3 minus 1 minus 6 into 0 0 I think there is a small mistake sorry minus 3 3 minus 2 minus 2 minus 2 now which is nothing but which equals P inverse of AP is equal to 1 by A in 5 plus 20 25 plus 15 40 minus 10 plus 10 0 minus 15 plus 15 0 minus 18 plus 18 0 minus 12 minus 12 minus 14 plus 18 plus 6 24 minus 24 0 3 plus 12 15 15 minus 15 0 minus 6 plus 6 0 minus 9 minus 15 minus 24 here is minus 24 here minus 24 and it is 40 40 0 0 0 minus 24 0 0 0 minus of 20 now which is nothing but 40 divided by 8 which is 5 0 0 0 minus 24 divided by 3 minus 3 0 0 minus 3 so here P inverse AP is nothing but the diagonal matrix which implies here we get P inverse AP is equal to D where this D is a diagonal matrix and the entries of this diagonal matrix are nothing but the eigenvalues of the matrix A. Since in previous in starting with this example we have find out the characteristic values of A and which are nothing but 5 minus 3 minus 3 and here if we find out P inverse AP then we get one diagonal matrix whose diagonal entries are 5 minus 3 and minus 3 and by the definition of diagonalization of the matrix a matrix A is said to be a diagonalizable matrix if there exists a non-singular matrix P such that P inverse AP will be equal to D where the diagonal entries of the matrix B are nothing but the eigenvalues of the matrix A then we say that the corresponding matrix A is a diagonalizable matrix so here A is a diagonalizable matrix and here is the Thank you for watching the lecture.